So I'm here today with Peter Woodhead, who contacted me because I'd done a presentation which some people watching this video might have seen about two interesting topics: the hollow Earth and the expanding Earth. And Peter had contacted me because he'd also been researching these topics, having become interested. So we're going to spend a good bit of time talking about that, and what Peter has ended up showing me today is, I think it's really extremely interesting, and he's kind of almost joined these two topics together, kind of, as you'll see as we discuss this. And the way that he's done this is very, I think, very sensible, and it explains a number of the anomalies, some of which we're going to try and go through today. And he's tied together that with some of the scientific research that he's discovered about, for example, the formation of planets. So we're going to talk about that, and we're going to talk about things like the dinosaurs and how that they could have walked the Earth when they, if they walked the Earth today, for example, they'd be too heavy and their joints would not work properly because they'd be too heavy, basically. So we're going to try and cover all of that, and I think hopefully you'll find this is an interesting presentation. So thanks for inviting me, Peter, and for your hospitality today.
Nice of you to come and indulge my little theory.
Well, absolutely. No, it's a great pleasure, and I think what you're showing me, as I say, is very, very interesting. So perhaps we'll start off then, and sort of if you can tell us a little bit about background, as much as you want to tell us.
Well, I've been researching several different ideas over the years. Most of them you might consider to be conspiracy theories, but such is life. That's what interests me. I hadn't really looked at the thought of a hollow Earth before about 12 months ago. And basically I'd been watching one of Richard's shows, Rich Planet, where he interviewed a guy called Keith Hunter. And he interested me because he was talking maths, which I'm quite interested in, and he was also talking about the ratio of units of length, which I think he was using a fathom, 6 feet.
Oh yeah.
And the multiples of those fathoms, and in relation to the circumference of the Earth. And although it was a bit baffling, it was interesting.
Yeah.
And it got me to thinking that, well, has the size of the Earth changed? He was looking back into antiquity, I don't know how far back, and he reckoned that the world then had a 360-day year, a 30-day month, and this figure of a fathom fitted perfectly into the circumference of the Earth, and that he'd noticed that we are out of sync with that now, having 365 days and a larger planet circumference. So it just got me thinking, and so as you do, I've been on the internet looking at different things. Came across the work of James Maxwell and Neil Adams, who've both done fantastic computer-generated images of our Earth going back in time and then forwards again, and the relationship of what is the continental area now and the new crust formed in the mid-sea ridges by volcanic action.
And I think that's one of the things where that's where you have to start looking at why the Earth is changing, because when they did, I think the key factor that Maxwell highlighted, and I think probably Neil Adams as well, is that when they did these oceanic surveys, there was no ocean floor which was older than 180 million years, I think was the figure.
Yeah.
So that was a bit of something they couldn't really explain, that the Earth was meant to be much older than 180 million years. So where had the other ocean floor gone? And so they came up with this idea of subduction, didn't they? That the older ocean floor was being subducted or under the continental shelf.
I think it was, I don't know if it was in the early 50s, a guy called Alfred Wegener, and he came up with this theory of continental drift, which is what we were. And so the theory of continental drift required, with a fixed size Earth,
Yeah.
it required somewhere for this new ocean crust to be disappearing. And so they came up with this theory of subduction,
Yeah.
which is the new, or rather the new-ish, if you like, seabed comes up against the continents and then is drawn underneath the continents. So then you get to have a fixed-sized Earth.
Yeah.
But what Adams and Maxwell say is it's not a fixed-sized Earth. There's no subduction, and the Earth is getting bigger, and this new crust that's being formed in the centre of the oceans is pushing apart and creating an expanding. I call it expanding. Neil Adams gets quite upset at the term expanding.
We're talking about that, yeah.
He insists that it's growing and that new mass is being created somehow. That's where I sort of lost the plot a little bit.
Because I think we need to pause on that, because this was one of the, if you go and look at the expanding Earth as a look at the evidence that James Maxwell has put together, it's pretty compelling that he's actually right, that the Earth is indeed expanding. Mm-hmm. And once you look at, because he's gone through all the geological records, and looked at the way that species have migrated and flora and fauna have migrated, and he's gone into a lot of detail, hasn't he?
He has, and he deserves the credit for that.
He does indeed, and I've looked at that and I've written to him. I think we've both written to him and exchanged emails with him. But as the key point is, when you talk about the expanding Earth, which we're going to go into more in a few minutes, is if it's expanding, how is it expanding? And then there are two possibilities: either we've got a constant mass there that's kind of inflating or whatever, or just expanding if you want, and the mass is not actually changing, or even Maxwell's talked about this, and Neil Adams talked about this. So they think the mass is actually increasing, and the primary reason why they think it's increasing is because of the gravity effects, isn't it? Which again we're going to talk about, which if I've understood that right, isn't it? They've based the idea of the increase in mass, connecting that to the increase in gravity, haven't they?
Yeah.
But then, of course, all the normal mainstream scientific community will say that's just nonsense, because mass just isn't created like that. How can this mass be created? And I think what you've done, Peter, from what you've shown me today, you've come up with a very good sort of explanation for the increase in gravity, but the mass staying the same.
So I found the images they'd created fabulous, basically, and compelling. You can hardly watch either of their videos and not think, well, that's got to be right.
Yeah.
But where it all falls down is when they get to the point of, well, where's all this mass come from? And I see the logic, and I thought along the same lines for a considerable length of time. But the increasing mass of the Earth, and as Neil Adams would say, the increasing mass of the Moon, are not compatible with maintaining a realistic orbit of the Moon and the Earth. Because if over the last 300 million years our mass has increased by a factor of 5, and probably a similar figure for the Moon, then using the simple equation of inverse square law of gravity,
Newton's equation,
you'd have these two objects that are getting bigger and bigger and attracting each other more and more, and it wouldn't have taken 300 million years for us to crash into each other.
Yeah.
So from that reasoning, you have to dispel the increase in mass, which is good because there's no realistic theory of where this mass comes from. They both stated that it's some kind of transfiguration of energy into mass, which they can't explain it. So I've dispelled with that in my theory. There's no need for any more mass. The increase in mass does explain the increase in gravity, but as we'll see later, I've got an explanation for why gravity was a quarter of today's value in the time of the dinosaurs.
Yeah. Okay then, Peter. So one of the mysteries that is not really, we see it as a mystery, but it's not really seen as a mystery so much by other people, is, for example, the size of the dinosaurs. These were huge land-based creatures, and these days the only creatures of that size, like the blue whale, for example, live in the oceans, where they have buoyancy, so they can have a larger overall body size. But again, if you do the maths, and I mean, we've talked about Stephen Hurl's book, haven't we? Dinosaurs: The Expanding Earth, and we both stumbled upon that, I think, under similar circumstances of looking at this expanding Earth research. And he points out in there, and he does some, because I think Stephen Hurl's an engineer by background, and I've got a software engineering background, as some people might know, and you're in the building trade, so you're used to dealing with heavy weights, aren't you?
Yeah.
And so on. What Hurl calculated was, he did some surface area and volume ratio calculations, and he said that, like, their knee joints could not possibly have worked with the strength of bone and the type of material that the bones are made of, which I think is fairly well known. They would not have been able to support their own weight. So we are then led to conclude, and also, for example, the size of various flora and fauna, which are much larger than, not just the dinosaurs. We've had insects, I think, that were 2 metres long and stuff, haven't we? They've got, I've talked about this in the Expanding Earth presentation that I did. So we've got those problems in nature to look at and to solve, and so some people have concluded, like us, that gravity was actually weaker then. The force of gravity was lower.
Yeah.
And so we then, as we said a few minutes ago, stuck with, well, if you've got a lower force of gravity, it means one way of getting that is to have less mass. But as we're going to see, it's not necessarily going to be like that, is it? So if you want to sort of add anything to that.
Yeah, I did struggle with this for a while. In fact, using the standard formula for the attraction of gravity between two objects, i.e. a dinosaur and the planet, if you go back to the reduced sized Earth when the dinosaurs inhabited it, if you take the centre of the Earth as being the centre of gravity, then you actually get a greater figure for the force of gravity in the time of the dinosaurs. However, it's a tricky one, because the simplified formula for the attraction due to gravity assumes it works great on a planetary scale, because the distances between them are huge. Whereas when you're actually stood on the surface of the attracting body, where actually is the attraction coming from?
Yeah.
And in the models that I've done, in the time of the dinosaurs, you can actually place the points of attraction to maybe 1,000 kilometres deep or 600 kilometres deep.
Right.
Yeah. But today, with the expanded planets, the point of attraction is actually 300 or 500 kilometres below our feet. So then, because it's an inverse square law, the figure under the equation was 4 times greater back then than it is now. Therefore, a quarter of the gravity.
Yeah.
Between the dinosaurs and the Earth, even though we're on a bigger Earth. The mass I'm contending is the same, but it's the point of attraction beneath our feet that makes the difference.
Yeah.
And it's easily shown by maths. It took me a while to get my head around it.
We're talking about the mantle being a shell, aren't we? So of some kind, and then the key concept here again that you've shown me today is that Max Lowe and Neil Adams and others of their ilk assume a solid all the way to the core, pretty much. Don't
it does account for the gravity, because you get a bigger mass of Earth and you get more gravity.
Yeah.
And I think where Max Lowe missed the point was he was using that simplified equation.
Yeah.
where you take the centre of the planet as being the centre of gravity.
Yeah.
And it just as I said, it gives you a figure in the era of the dinosaurs of 3 times greater than now, not a quarter of.
Yeah. Yeah.
And so he dismissed that very early on, whereas what he needed to do was perhaps expand his search for the real centre of attraction, which is not the centre of the planet.
Right, and then you were telling me that quite a lot of this has come together in your mind, fairly recently. I think you started looking at this about a year ago, was it, or something?
Yeah, but really only got round to polishing off the maths in the last few weeks. It's easy just to take even Maxlow and Adams's compelling videos. It's easy to just assume that's where we're up to. And what I think I've done is take it a step further and said that's not the extent of what we can deduce.
Yeah.
We can deduce things to make it all work, because they were left sort of with having done all the hard work. I'm not claiming to have done anything that they haven't done. It's just they hit a wall, and now we're on the other side of that wall, and we can explain.
And what you showed to me earlier, I think, is one of the key starting points, and that's this article about the way that planets are formed. Although the article that you showed me is not specifically about planetary formation, it really is. I don't know if you mentioned that, but it alludes to planetary formation because they've observed this disk of material around this other star, haven't they?
These astronomers are looking at an accretion zone of a newly formed sun, and what they're saying is that the birthplace, if you like, of what will become planets in that star's system. So what they're saying is, I'll read this to you.
Yeah.
That they've imaged a snow line in the accretion disk surrounding the sun-like star Pt.1-3.Andrew, a young star 170 light years from Earth. They state that starting from the star and moving outwards, water is the first to freeze, forming the first snow line. Further out from the star, as the temperature drops, more exotic molecules can freeze and turn to snow, such as carbon dioxide, methane and carbon monoxide. So they're suggesting that the area of the ice, water being frozen to ice, is in the area of an orbit of what might eventually be forming an Earth-like planet. So that turned on my head everything I thought I knew about formation of our planet, because as you learn in school, you think back to what and the textbooks, they showed some kind of boiling hell on earth scenario where everything's hitting each other and high temperatures. And what I realised was, well, out in space it's pretty cold, minus 273 absolute zero. So this ice and some of these such as methane, they're not freezing at zero, they're freezing at minus 100 and something. So I'm thinking, well, there's no ambient temperature to create all this heat that we have in the textbooks. So I thought, well, what would our Earth be like if it was newly formed? And if it was mostly, well, a high percentage water, and all the other stuff that we've got on our planet was in the mix, if you like, what would it be like? And I think for a long time it's going to be very cold. Now, as I think we're going to be going on to soon, NASA did an experiment on the space station.
This is great, when you showed me this. I've
Yeah,
never seen this before.
It's a bit light-hearted. I don't know what made them think of it.
Yeah.
But as you'll see, I think you're going to put it on. You play the video, and they showed a revolving golf ball-sized lump of water. Mm-hmm. Yeah, sphere of water, because it's weight. Yeah.
It's on the International Space Station, isn't it?
So then they inject that first with some air bubbles, and as it's spinning, the bubbles all migrate to the centre. Then they inject some tea leaves,
yeah.
and the tea leaves migrate to the outside. And I thought, well, that's turning on everything on its head that I've been taught,
yes.
because we're supposed to have not a molten, but an iron core to our planet.
That's right.
And I thought, well, if this is what happens in space, then the heavy stuff goes to the outside and the light stuff goes to the inside.
Here we have a rotating sphere of water about 25 millimeters in diameter, and inside this sphere are a whole bunch of little tiny air bubbles. And we will see what the angular acceleration due to rotation does to these air bubbles as a function of time. What you are observing are the bubbles moving to the center axis of rotation. As a function of time, they will form this rather tightly packed bubble core. These bubbles are kept from coalescing from a small amount of added surfactant to the water. Here we have a rotating sphere filled with bubbles and tea leaves, and as expected, the bubbles go to the center and the tea leaves go to the outside edge, along with a few chunks of orange peel. Here we have a rotating sphere with bubbles and chunks from breaking up a small vitamin tablet. And the bubbles go to the center core, but the vitamin chunks seem to stay in their location dispersed through the sphere. And from this we deduced that the vitamin chunks have a density near that of water.
And it just made me pull the ideas together that in this TW hydrate, when it starts to form its Earth-like planet, the solids are going to go to the outside and form a crust, and the inside, which is frozen methane and mostly water in the form of a sort of a slush, for want of a better word.
We're trying to come up with a good word.
Yeah, anybody who's got a better word for slush.